Okay, yes. So we had a presentation about NV centers, two about silicon. So now let's talk a little bit about superconducting qubits, but let me shortly introduce our company. Our company was founded in 2017, and we work in the space of simulating materials and chemical processes. So we started working with companies like BASF, Bosch, and Merck, and then also later with many academic institutions. And today, we still work with BASF, Bosch, and Merck. And we work on the simulation topics on conventional computing. So some people might know this type of topics like density functional theory and similar things. But of course, if you want to calculate properties of materials, you want to solve the laws of quantum mechanics, this is intrinsically linked to quantum computing, is one of the topics that you want to solve using quantum computers. And so we work, of course, on using quantum computers for this simulation topic. And therefore, we also have a vast amount of research grants, and I want to thank our research, the funding agencies, the German Ministry of Research and Science, German Ministry of Economy and Climate, of course the EU, for all the support. But now, here we are in the session of materials, emerging materials for quantum computers, so to say. And now, superconducting qubits are actually already being used. So you can use, via the cloud, superconducting qubits today. They have substantial limitations, but it is already like a huge progress that they can be used. And so what I'm going to do is actually I'm going to talk about what happens if you use the existing superconducting qubits, how we see various errors, so noise and problems when you run an algorithm, and how this relates to material properties that are well known in superconducting qubits and should be improved probably as we go to the future and want to really go to scaling qubits to millions and millions of qubits. So let's look a little bit at this just as a reminder. Again, very shortly, the classical bit. The classical bit can be in the state 0 and 1. You can depict this as an arrow where the classical bit has the two states. The arrow points down and arrow points up. The qubit, the quantum mechanical bit, can be in two states at once, so in 0 and 1 at once. It's very mysterious, but as long as you only talk about a single qubit, you can depict this again as an arrow on a kind of sphere, and now this arrow can point in every direction. And I wanted to show this to explain a little bit what you see next when you run an actual quantum computer. So here we have an actual run. This was done on IBM Q. And I explain in a second what you see. But I also want to say that it is really fantastic that today, for example, from IBM, you can get access in a quite routine fashion to quantum computers to actually use them and see like their day-to-day performance. Even if this performance is limited, this is super helpful for the community, as you will also see, because we can see how things really perform in practice. And so what we did is here we ran kind of a succession of 4 gates. And these 4 gates are, you take the qubit, you start up, and then you rotate pi half, another pi half, another pi half, and another pi half. This means if you do this, you should have rotated all the way back to the top. Meaning, if we do this in succession, so we call this a Trotter step for some historical reason, I would say, and then we do this again and again and again, and you should see, you start in 1, and nothing should happen, in principle. So ideally, if the quantum computer would exactly perform in a perfect fashion, nothing should happen, because you rotate once around the sphere and then look at it. But then, what happens is you actually see this really beautiful, I have to say, oscillation. And when we saw this, we really liked it, I have to say, because we do a lot of error modeling for quantum computers. And one typical model is called an over-rotation. So you say, okay, you do not quite match the angle that you want to have. And here, this was to some extent a little bit a hypothetical thing because people hadn't really nicely measured this over-rotation effect. It was kind of clear that it should happen. And here we see it really in a beautiful way. Let me also point out, if you count the overall number of gates, it's 800. Having one overall oscillation over 800 gates is really solid fidelities. So that's a well-calibrated quantum computer at this stage. And we actually know very well why this over-rotation happens, because here again depicted the qubit with the states 0 and 1, this time in this kind of quantum mechanical level structure. And you use kind of a microwave field to address exactly this energy splitting. And if you're not hitting it precisely, you're getting these over-rotations. And similarly, this was an over-rotation basically where we measure in Z direction. Now we measure in X direction. Actually, we do nothing on the quantum computer. So we just make idling gates. So each of these steps are somewhere between, I don't know, 5 or 6 or whatever idling gates. And if you do nothing and measure in X direction, actually there is an external clock that measures in some sense an internal rotation speed of your quantum computer, which is again related to this frequency splitting of your qubit. And if this external clock is off, you again effectively see some effective oscillations, not quite as clear. So this oscillation does not have to be only around one axis, meaning we could not quite immediately fit it. Can also differ from qubit to qubit. A bit more complicated, but also pretty clear where it comes from. This qubit splitting has shifted and is not quite there where it should be. And now let's come a little bit. So this is what we see when we run quantum computers. Let's come a little bit to where this comes from and what, or let's say one of the known effects. Yeah, I mean, currently quantum computing providers do not, of course, provide like detailed descriptions anymore of all the things that we do. So I want to discuss one effect that is historically well known and clearly, I mean, very likely still important today. And let's shortly talk about superconducting qubits. The current generation of superconducting qubits are very similar to just a superconducting antenna. So imagine you bring like an aluminum strip on top of a silicon wafer, and this would just be an antenna. An antenna alone would not be enough to run a quantum computer. What you need is a nonlinear element, and this is the Joseph junction where you put in some aluminum oxide. And then if you are at, for example, 20 millikelvin, the aluminum is superconducting, the aluminum oxide is insulating, superconductor, insulator, superconductor, that's the Joseph junction. And with that, you have with that, you have, in some sense, a qubit. Yeah? Up here, you would have a resonator, meaning an antenna, which is, let's say, one kind of resonance frequencies, and this would mean all the energy levels have the same splitting. Out of this, you cannot build a qubit because you cannot address two levels, because you always, if you use some external kind of driving field, you address all the levels. So you put in some nonlinear elements, now these levels change, and now you can address two of them. And in practice, of course, if you kind of, I don't know. I mean, there are various ways to kind of produce this, but the reason why this material has been chosen and why people use it is because putting in the aluminum oxide is a very simple step and a very controlled step. So you put on your aluminum, then you just let it you put the oxide on, which is very simple because for aluminium, the oxidation is a very controlled process. And I think most people know this, that aluminium grows a very controlled oxide, which is beautiful, of course. And that's why, this is the way we build superconducting qubits. And at this point, at least, and then, of course, you have your oxide, then you put another layer of superconductor on top, and then, of course, I mean, sooner or later, this is going to oxidize it well. But here you now have your oxide layer which forms your junction. And this is really a very nice process. However, clearly an oxide is always an amorphous material, meaning you do have aluminum and oxide atoms, and you can have situations where these oxide atoms jump between different positions. or let's say fundamentally have the possibility to jump between energetically very different kind of states in this material. And you can depict this as like a double well potential. I mean, it doesn't have to be exactly symmetric, it can be slightly off-symmetric, all types of things have been observed. And now you have basically a two-level system within your oxide. And what does this do? So now you have your qubit, your superconductor, and here your oxide, and an atom can jump between two positions. This couples to the the kind of electrostatic field that drops across this capacitance. And this electric field couples again to your qubit. And then what this leads to is that basically depending on the position of this atom, the energy splitting of your qubit changes kind of a little bit. And this kind of effect happens on all time scales. Yeah? So, I mean, it has a structure very similar to the famous 1/f noise. So, on every time scale, you have kind of slight fluctuations of your qubit splitting. And you can have relatively, I mean, on the scale of kind of errors that you want, relatively large kind of changes on the scales of minutes or seconds. And therefore, kind of in principle, you have to recalibrate quite often, but it's very difficult to keep this under control. But again, aluminium is used because it already provides a quite clean oxide, meaning this is a quite challenging problem where it's not super clear to me if progress can fundamentally be made or if this problem has to be fixed through calibration or other means or through completely new materials. And with this, let's now actually very shortly, I mean, I'm at the end and I think the session should come to an end. Let me shortly show how this looks if you run an actual algorithm. So we are in the space of running algorithms, you know, related to chemistry. And one very obvious application that's quite popular in that space is you want to calculate the spectrum of a nuclear magnetic resonance experiment. This means basically, in practice, you would take some molecules, put them in some liquid and a magnetic field, shoot some microwaves at them, and measure what microwaves come out, and then you would see some kind of spectrum of microwave radiation. We can put this on the quantum computer by taking these molecules, calculating an effective spin Hamiltonian, translating this into kind of gates that we run on the quantum computer, extract certain quantities by measuring them and getting a similar spectrum. And now here I show you a spectrum calculated for a small molecule on 3 different days. So the black line, as you see in all 3 plots, is always the same. So this is basically where we just solve this directly. It's a small example, meaning we can easily solve it on a conventional computer. It's not a problem. And the orange lines are measured on a quantum computer. Already very nice. You clearly see the relationship between what you want to have and what you get. But you also see that from day to day, the performance is different. All these peaks are slightly off. The height is always a little different. And clearly this comes from these quasi-static fluctuations where you have kind of small changes in the qubit parameters from one day to another, from 1 hour to another, from 1 minute to another, and even from 1 second to another. And if people would feel inspired to work on this problem, I mean, it's a super difficult problem, so I don't know how it's going to be solved, but I think this could be really helpful. And as we look forward to scaling superconducting qubits to millions, I also feel it might be necessary to, on a more fundamentally level, solve this. And with that, I'm at the end. Thanks.
Thank you very much, Michael.